Okay, welcome back. So we are working on lecture 7, soil compactions. In this lecture, we will learn about how to establish compaction curve from given laboratory test results. Also, we will learn how to apply compaction curves to engineering designs. So the topic of compactions, soil compactions, is highly tied with the understanding of compaction curves. So soil compactions, what is it? So the definitions is the densifications of the fill material for constructions. So any like fill material could be clay, could be sand, could be silt, could be like naturally occur material that you bring from other job sites, or like some like man-made material that you have sift through to a particular gradations. So for design, well grade, fully graded gravel, or like only like a clay only type of materials. Um, so how to densify those materials for constructions? That's just the topic of soil compactions. Um, and the need for that is we try to reduce the void ratios at almost a constant water content. So water content is very important. Throughout this lecture, we talk about that. When we talk about compactions, it's all about water, water, and water. So through the compactions progress, the volume of air will reduce. Um, so the idea here is we have, remember from our phase uh, relationships, phase diagram, you have air, water, you have solid. You know the total volume. So this is before compactions. And after your soil being compacted, so what has changed? So the water actually hasn't changed, and this solid hasn't changed. But what happened is we're reducing the amount of the air. So this is after compactions. So now the amount of air has reduced. So solids still stay the same as water, but the air has been reduced. So now this is your updated total volume. And we have a change of volumes because of the reductions of the air. So we have done that because the volume of void has decreased. Well, remember the volume of void is equals to volume of air plus the volume of water. So this has decreased, and the volume of water still the same, as such that the volume of void has decreased. So that's the general ideas of soil compactions. And imagine that for any kind of like civil engineering projects, the very last grading. So your foundations, either deep foundation or shallow foundations, you work underneath the ground, but like the very last leaf of a backfill. So you get to the almost like your final grade, and that final grade material, you have controls on the density, which means like you want the final grade to a particular density that uh, to 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 fit your structure, such that like you can um, control the mechanical behavior in terms of like strength, and also in terms of compressibility through the use of compactions. Uh, so um, that is one of the objective of what we're trying to do. Uh, by doing soil compactions, it can improve the soil properties for constructions. So you can either like increase the stiffness, so the strength will increase. And one of such examples is pavement design. So this is your subgrade soil that before you lay down all the pavement materials. So you can control the you want to control the density of your subgrade soil, your very last grade of soil, such that like the soil is strong enough to support all the loading above it. So including the loading from the pavement and also uh, the expected loading from the surcharge. Could be from the building, could be from traffic loadings like the vehicles driving through your highway pavement, or like it says the final pavement for construction of buildings. So that's one purpose. The other purpose is we can, by through the compactions, we can decrease the hydraulic conductivity. So even the same material, remember like back to lecture 3, we talk about the soil hydraulics, like clay has much lower hydraulic conductivities than a material like sand or gravel. But even the same material, the same sand or the same clay, right? Uh, if you compact on it, if you increase the density, you will lower the hydraulic conductivity. So we do want to control the density such that when we build on our levee or dams on this picture on the right hand side, so when we construct this like earth structure here, the density of each layers after layers, uh, the design part of the design is to determine what kind of density is it to achieve the hydraulic conductivity we want. Very likely, we want to have a low hydraulic conductivity such that we can slow down the seepage going through the earth structure. Okay, here, so this slide shows you how the soil compactions is done on the field. So you have open sites here preparing for the final grade, and you have a heat food compactor passing through uh, the 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 very last layer of field material. So as the compactor passing through the site, the weight of the machines is doing the soil compactions. And here's a closer look on what happens on those sheep food. So those are the kind of acting like a hammer when you're like passing through the soils. So when you contact the soils with the heavy weight of the machines, so the final grading, the topmost layer of soil now is being compact. Remember, the key, the key, or the key concept, or if you just use one sentence to define soil compactions, it is the reductions of the air volume. So what happens is all those like sheet food or those compaction effort pounding on the soil will densify by reducing the air volume. So that's the key concept. The compaction effort is not the only like a factors. When we talk about soil compactions, another very important factors is water. Water is very important. So if we just talk about compaction effort, you can bring a very heavy machines. If you need more compaction effort, you can bring a if you want to increase the compaction effort, you can increase the weight of the compaction machines or the compaction loading, or like you done it by compressing or compacting the site by the machines or the vehicles like going through the site more and more times or more pass. So remember, like we do this because we want to densify the soil. So there's a certain density we want to achieve. And to do that is very logical that you do it by increasing the compaction effort, which means like, either increasing the weight of the machines or pass of the machines like passing through the site more times. So with more pass, more compaction effort. But like, that is not enough. Just increasing the the compaction effort is not enough for us to get to the desired density in some case. Uh, what being important too is the water content on the site. So you see what happens here is you have if you decide if you know you deal with the geotech engineers, if you find out like the soil is too dry, then it is logical that you add water. If this is too wet, you may want to, uh, let the solar energy, wait for the sun to dry up, expose the soil under the sun, and then let the soil dry up a little bit until you get to the water content you want. And then with the correct water content and also enough compaction effort, that's how the job get done. So don't forget about it. The water is very important. Okay, for the geotech practice in soil compactions. Okay, for soil compactions, geotech practice. So let's look at the big picture. So you have a job site. Um, at the field, you have the field material for constructions, either for clay, sand, or silt. So now you have the materials, and you know that for your design, you need to compact your final grade to certain density, and how the whole thing like are being operate. So first you have the material, then what you will do, you will ship the material to the lab. So you will perform what we call the soil compaction test. So the purpose for that is it is for the soil properties mainly related to the compactions behavior, compactions performance for the materials. So you will get the soil property characterizations in the lab. So what you need is to get two parameters. First is the gamma D, which is the maximum dry unit weight. So the gamma terms over there stand for the dry unit weight, and the D terms over there stand for um, the dry, being like a dry conditions. And to be more precise, it should be gamma D max. So gamma D max means the maximum dry unit weight. And remember, very important for soil compactions is about the water content. So the second parameters we need from the soil compaction test is the optimal water content. So it's just the water content that allows you to achieve maximum dry unit weight. So these two parameters always come together. So you have the material from the field, you ship it to the lab for the compaction test. So after the test, we'll talk about like the soil compaction test in greater details later. But after the test, you expect to get two parameters. So now you have these two parameters, you can bring it back to the field. So now you have the reference, you have the test results with you, such that you can allow you to do the quality check for compaction effort in the field. So this is how like the geotech work deal with in terms of soil compactions. So let's look at those like laboratory tests. We have the manual type of compaction test, and also we could have the automatic type of testing equipments. And these are for us to investigate the effect of compactions, and those tests are necessary to be done in a more controlled environments in the lab. So and here's some like details of those testing, and remember like what one like important parameters that we want to obtain is the unit weight, and the definition of the unit weight is the weight over the volume. So pretty much like the whole concept of this test is you want to weight how heavy is the soil with a confined volumes, and the volumes is standardized by the ASTM standards. So the best reference for those conversion tests is ASTM D9 698 and also D 1557. Those ASTM standards are available on Canvax. So if you want to like read that in better details, please go to Canvax. And also highly recommends this YouTube clip that you can. It's just like a 15 minutes. Go ahead to watch them on YouTube's, and there will be some I think it's some students from University of Missouri. They will guide you through, they walk you through how those tests are being performed. So here is not the best time to talk about those tests in details, because when you take the geotech lab class, actually you will in the lab, and then like hopefully we'll go back to the lab, and in the lab you will work actually hands-only work on those testing procedures. So that's the best chance for you to actually like not just visually to see the test how being done, but actually you work through it, and you will learn all the details about how to measure the maximum dry unit weight and water content. But what I want you to get out from here now is uh, the key concept is you want to find out how much weight to fit in a confined volume at different water content, such that you can form the compaction curve. So this for STM standard, this is the volume. So you prepare pretty much like you prepare the soils here by adding different amount of water. So it's not just one test; it's at least like 5 to 6 tests, and but each test you will different amount of water to add on, and then like you will do the compactions either uh, manually here, or you do it automatically here. So with different like a type of compaction effort, and then like at the end of the day, then you will wait. Then you will get the volume, and then now you measure the rate, then you can find out the unit weight at different water content. So that's the key concept of those compression tests. And there's two ASTM standard. One is for standard porter, and this one is for the modified porter. And again, like the best way for you to learn here now for this course is go ahead uh to watch the YouTube clip. And like later on later semester, then we go to the lab, and actually you will spend a couple hours to work on those tests. So after those compaction tests, then we will have enough data to prepare the compaction curve, and which is the most important part for this lecture, understanding the compaction curve. So again, this is not just like a one test allows you to construct the compaction curve. Is at least like a 5 to 6 tests. So what you will do is you will have 5 to 6 compaction tests right there. For example, 5 tests here now, and each test you will have a target water content, So WC stands for water content. So this is how to be, again, like, this is how to mix your soil at the beginning. You have your target water content, and you have your soil, dry soil to start with. Uh, then, like, you can mix your soil. So target water content, for examples, I make up the number here. The actual well, the number, the testing number, you need to based on the soil type, and as a geotech, you're advised to lab what type of water content you will be testing on. But ASTM standard may give you some like an initial guideline to start with. But those target water content is something that, like, you need to, as a geotech, you need to understand uh, the soil that you're working on, and then you need to come up with those target water content. But anyways, this one, let's for example, is 10%, 15%, and 20%, and 25%, and 30%. Like, after you mix the soils, and then you do all the compaction tests, you go through all the steps here now, then you can measure the weight of it. So you know the weight, you know the volumes. Then for each test, you can find out total unit weight, the total unit weight corresponding to each test. And after you do the compactions, you extrude out the soil samples. So this being extruded out from the mold. So this is the same mold with the as the standard volumes. After you extrude out the soils, you would take out some soils, and then for a water content test. So pretty much they try to measure the actual moisture content when you finish the test. So after you measure total unit weight, then you can find out the measure water content. So this measure water content should be very close to your target. So you get like a 10% here, so you may get something like a 9.5% or 10.5%, maybe some discrepancy, but like should be off much, depends on how well you mix the soil and stuff like that. So this will be a little bit off, but at the end of the day, you get your measure water content. So after you have your measure water content, then you can use that number to calculate the dry unit weight. So remember from our phase, like our relationships, back to lecture one, the dry unit weight will be equals to your total unit weight, which you calculate there, divided by 1 plus water content, to measure the water content. So that counts, you get your dry unit weight. So after like you go through all this procedure from the lab, then now you can have your y-axis. So this is your y-axis here, and your x-axis is your measured water content. So this is your measured water content right there. That will become the compaction curve of your x-axis. And you have 5 tests right there. So you have like a 5 coordinate pairs right there, 1, 2, 3, 4, 5 xy coordinates. Then you can form your compaction curve. You may get something like this. So 5 points, 6 points, you need to have at least like a 5 points to define a curve. So after you plot out those like a data points, then you can draw the curve. And the maximum point on the curve, that will give you the parameters you need. Remember how we mentioned about it? What we need is 2 key parameters, the maximum dry unit weight and also the optimal water content. So those 2 points corresponding to the maximum points on this compaction curve. So here, the x coordinates of this maximum point give you the optimum water content. And the corresponding y-axis readings give you the maximum dry unit rate. So the gamma D max. So this point is very important, and understanding how to get that point is very important too. So the unit of maximum dry unit rate could be something like pounds per cubic feet, or kilonewtons per meter cubes. And the x-axis is water content, so it's the percentage. So furthermore, the maximum point also divided the compaction curve into two parts. So the right-hand side to the maximum points, we call that to be wet of optimums. And the left-hand side of the curve, we call that to be dry of optimum. So this optimum point here is very important. So what is compaction curve? So compaction, the compactions curve pretty much is representing the compaction test results. So once you're able to obtain your compaction test results there, then you can construct this curve. And this curve is very important for later on, like our geotech design. So per the ASTM standard, there's two different type of compaction tests. So for ASTM D698, that is the standard porter test. And also there's a ASTM D1557, that is what we call the modified porter test. So why we need two tests or what are the difference between the two tests first? So this table summarize the difference between the two. So first start with the weight. So this weight here means the hammer that when you're performing the test. So standard porter start with a lighter hammers, which is like a 5.5 pounds, and standard porter also uh, the length. So this is supposed to be length, not the not the D. So the length of the standard porter is 12 inch, and like the length also define like how far or how high is each like a hammer stroke to pound on the soils. So the standard porter is 12 inch, and the modified porter is much like a larger stroke, but like much longer strokes. You get 18 inch. And this N here is like a number of pounds or number of blow for each layers. So this is the layers. So standard porters, you have 3 layers. So what does it mean is, again, this is the confined volumes that you work on. So per ASTM standard, the volume is 1/30 cubic feet. And standard porter, you have like a 3 layers to fill up the confined mold, or the, so let me use other color here. So this is the mold, and standard porters, you have like a 3 layers. So first, second, and third, and each layers you put on pretty much like I use the hammer to hammer the layers 25 times. So first layer 25 times with the 5.5 pounds hammers, and each like a drops is 12 inch. So 25, 25, 25. So 3 times 3 layers. 25 times like a 3 layers for the standard porter. And all those informations here give you the amount of energy that you kind of like a pound on or like a put on the compaction molds for the standard porter with this number. And a modified porter, very similar, but now you have actually modified porter is the same compaction mode, so same volume, but now the hammer is heavier and also longer length with the same amount of number of like balls each layers. But this time your layers is 5 layers instead of 3. So this is standard and this is modified. So more than 5 layers, the same volumes, but you will have like a 5 layer there. 5 layers, and then each layer is the same number of blow, 25. You hit like this layer 25 times, and then you put on soils. Uh, you hit another 25 times, and you put on the soils. You hit another 25 times, so on and so forth, until you finish your 5 layers. So that will be the also the lab test you'll be working on with your group when you take the C360H Geotech lab class. And this modified porter, as you can imagine, is like a more layers and heavier hammers, a longer hammers, so you have a higher amount of energy that you invested in the same confined volumes. So why we need like this two different tests? And actually, like before World War II, everyone just doing the standard porter, but because uh, uh, like during the Second World War and after the Second World War, the demand of constructions in terms of the size of the structure and also the loading that like we carry on, particularly like the wartime during the war times, more heavier aircraft that need to carry like more and more like loadings, including the bomb that they need to carry. So they need to construct airport like one way with that can handle the loading from the aircraft, such that like they need to advance the technology to find out ways to make their pavements stronger, to such that the aircraft can take off from the one way. So those kind of like that very desperate time, people come up with like a new like compaction effort and compaction method, and then like this modified compaction test is part of the technology developed during that time. So that's why like we have this modified test, and on Canvas I upload PowerPoint presentations that like documents like the developments or all this history geotech this like all this fun geotech history behind our business. So feel free to read that on presentations. It's quite fun to know the facts behind what's going on and why we and what were the history behind us and why we do the things the ways that we are doing now. So yeah, very interesting read. So feel free to read it. It's available on Canfax. But like at this course, my expectations, my what I need you to at least understand is the meaning behind standard and modified porter tests. So the one very simple concept is modified uh, porter test means a higher compaction effort. Higher compaction effort. So compaction effort, how would that represent on a compaction curve? So again, this is compaction curve again. The x-axis for compaction curve is the water content, and the y-axis of the compaction curve is the dry unit weight. It's not total unit weight, but it's the dry unit weight. So we have two type of compaction efforts from the lab, right? We have the standard porter, and also we have the modified porter. So with the standard porter, we got a compaction curve like this. And now imagine you have the same soils, but you repeat the test with the modified porter testing equipments. So now, how would the compaction curve look like relative to the standard porter curve? So if you're able to do this, that means you understand this, and that's like what I require you to able to do for this class is understand the concept behind, and you can like communicate or represent your understanding on engineering representations for this topic, which is the compaction curves. So the modified Porter, if you relative to standard Porters, uh, the curve, oops, the curve will look like this. So you're at the upper left corner. That's where the modified compression curve locate. And each curve, you can identify the optimum point, which gives you the corresponding maximum dry unit weight and also the optimum water content. So if you increase your compaction effort, right? So the maximum dry unit weight and optimum water content will change when you like using different hammers with different compaction efforts. So this is the optimum water content. So each curve has its own corresponding maximum dry unit weight and optimum water content. And which also tells you, so with this two curves right there, which also tells you if you like whoops, this is not very good. If you increase the compaction effort, this is what you can predict. Is you would increase or like how's the optimum go. So this way is increasing compaction effort. So you can project that like if you keep increasing the compaction effort in the lab, which corresponding in the field, you will always go to this direction. So you pretty much you keep going this directions by increasing the compaction effort. You keep going that way, that way, and that way. And this line here is called the line of optimums. So that's the key concept here is you, now you have the standard modified portals help you to project, whereas like the next compaction curve will go if you increase the compaction effort. Okay. Okay, 100% saturation line. So for compression curve, we learned previously the x-axis is the water content, and the y-axis is the dry unit weight. And this is our compression curve. And we learned that previously, if we keep increasing the compression effort, the compression curve will move that way. We will keep increasing, you will keep on going this way and this way. And in fact, experimentally, we have already have proof that there's called an asymptotes, kind of like this, which means if you keep increasing the compression effort, you will keep the curve will keep going your upper left corner, but it never on the right hand side of the curve, it never touch this asymptote lines. What we call this to be the 100% saturation line. So theoretically, what happens is if you keep on compacting a soil, the soil samples, or like the soils on the field, what happens is you will getting if you keep compact on it, you will keep getting close to the 100% saturations, but you're never able to achieve 100% saturations. Because why? Because think about what is the fundamental definitions of soil compactions. It is the reductions of the air volumes. So if you keep compacting on it, you keep reducing on the air void, but you're never able to get rid of all the air void. So that's why you're never able to achieve the 100% saturations. So if you want to achieve 100% saturations, just compaction is not enough. Eventually, your compaction effort will be so great that you may just destroy the solid particles, but still like the air void that get trapped within the solid particles by compactions only. You cannot totally expel all the air void, but you can get close to it. So this 100% saturation line, we can actually like on a compaction curve, it'll be nice for us to able to plot it out too. So you kind of like a boundary to tell us if you increase your compaction effort, where you get close to, but you never crossing it. So kind of like an extra boundary, and we can prove this 100% saturation equations. Uh, so I borrowed this diagram on the this figures on the right hand side, which is exactly from your lecture one. Remember back to the phase relationships lecture, we try to express this phase diagram with the terminology that we've learned, void ratios, and also G sub S, which is the specific gravity, and also the unit weight of water. So, and also back to lecture one, I asked you to go home to practice whether you can, from a scratch paper, you can express a phase diagram with all this terminology, with your understanding on the meaning of them or the definitions of them. So now this becomes useful for us. The goal here now is we want to set up the equations for the 100% saturation line. So this line is under the solid compaction curve with the y-axis to be the drawing rate and the x-axis to be water content. So end up we want to set up our equations. So the goal here is set up the equations. Simple equations is y equals mx plus c, right? A linear not a linear equations, or maybe like this could be a curve, so maybe y or functions of x. So your y-axis now is the unit weight of functions of the water content. That's what kind of equate. That's the type of equations we want to set up, and to achieve that, we make use of our phase relationships diagram. So here, uh, we know the definitions of. We start with the dry unit weight because that's our y-axis. We know the definitions of dry unit weight is the weight of the solid divided by the total volumes. So through this phase diagram, um, the weight of the solid is G sub S times the gamma W. If you want to know, how we set up this phase diagram, you can go back to lecture one. And the total volume here is 1 plus y ratios. So this is 1 plus 1 y ratios. So this gives us equation one. And we also, there's another very useful equations we can use, which is, this is the way that I try to record this, is George Washington's. So the G sub S times the water contents is equals to a soil engineers. So the saturations times the void ratios. And this is 100% saturation line. So this is equal to 1 because saturation is equal to 100%. So the void ratios is equals to G sub S times the water content. So this equation is 2. So now if we substitute equations 2 back to equation 1, then we will have the unit weight equals to G sub S times the unit weight of water divided by 1 plus G sub S times water content. So this is exactly what we want. And this is the equations for the 100% saturation line on the compaction curve, or along with the compaction curve. So this achieve what we want to do because this is our y and this is our x. So y is a functions of the x, which is the drying rate is a functions of the water content, and the g sub s is a constant, and the unit weight of water is a constant, which is 62.4 pounds per cubic feet, and g sub s, the specific property, is the soil properties. So different type of soils you're compacting on, you will have a different g sub s. Okay, furthermore, so the compaction curve is also depends on the soil types. So the compaction curve also depends on. So you know that so this give a very good like a demonstrations. So if you have a clay type, if you have a clay type of materials, the compaction curve will be here. And again, this is the 100% saturation line for all different type of soil. So this is a 100% saturation line. So clay, you know that like you can hold relatively more water and achieve a relatively less dry unit weight. Um, so the clay curve will be here. So you'll be really good. Clay will be really good for ideal material for reducing hydraulic conductivities because it can hold more water. And the other extremes will be here on the curve is the well-graded sand. So sand, the capability to hold up with water will be less, so the water content will be less. But sand is a kind of like a much stiffer material than clay, so we will expect that you can achieve much higher dry unit weight or dry density. So that's why you are on the upper left-hand corner. So it depends on your design. With your understanding as a geotechnical engineers, then you can advise your clients or like your design. You can specify what type of material you will recommend for your project. For example, if you your project if you favor strength performance, for example, you're doing a nuclear plant or you're building on like the final grade for hospitals building that you need to sustain high loading demand from earthquake design, then where it makes sense that you use a well-graded sand as your final grade material. You will specify like a relatively high compactions density for that. The other case, for example, you have a dam or levee to build. You want to slow down the seepage of the waterfall. Then you won't make sense to use gravel as the material to fill up the fill material for your levees because the water kind of like a freely drain through it. So but like you want to slow down the seepage, so it makes sense to use clay material. So you specify you work with construction management, you specify like the fill material to be clayly type of soil. So with your geotech understanding, you will help you to do a design in specifications. So also like you realize the details is instead of sand, oops, sorry. There's a difference between well grade versus poorly graded. So those type of terminology, like this hopefully this all makes sense to you. Well grade means like the sand you have good representations of all the size that you have across the grain size distributions, versus poorly graded material which you only have one dominance type of like particles. So when we come with density, when you want to achieve higher density. So it will make sense that the well-grained material, where you have the small grain size to fill up the gap between the larger grain size when they compact or when they pack together. So that's why well-grade sand served the best in terms of you want to achieve the maximum density. or the highest density possible. So again, like a compaction curve, the expectations of that, or like the anticipated like compaction behavior will be depends on the salt type too. So for design, again, like furthermore, like uh, we also need to think of the water content you talk about. So the salt type matter based on what you want to achieve, and the water content also like affects your soil performance or your last grade or your or earth material that you pick, what kind of like outcome you want to have is not only because of the soil type and also the water contents being important. So for examples, this is your compaction curve again. And after you establish the compaction curve, what being most important is the optimum point, which is the maximum joining rate and optimum water content. So this is what you come back from the labs, a compaction curve. But as geotechnical engineers, you need to specify specific water content that on the site you want the constructions to be done at, such that like you give the performance you want. So some project, some design, you may like a favor, or you may like a decide to have a better strength performance. And the past research have tell us the strength is depends on water content, and you will have the maximum strength that is a little bit dry of the optimums. Remember we talked about this before too. So if this is like a left-hand side to your optimums, this is the dry of optimums. And if it is like a right-hand side to optimums, then that will be the wet of optimums. And we know that the strength is highest when this is just dry of optimum. So if that happens, you may want to specify the design for the compactions to be done at a water content a little bit dry to optimums. So you may want to specification. So the design parameter times is just like it's like one sentence of the writing, but you need to specify like what kind of water content you want to achieve. So you may want to do something like this. So this is just an examples. So the water content you may want to uh, specify at maybe because you want to be drier than less than that, maybe something like a -6% to positive like a 1%. A typical design, if you don't like highly specify on the strength or the hydraulic conductivity performance, typicals like a design you will specify it between like a -3 to +3% kind of like a water content design. So which means like when you have a compaction curve, this is the optimal water contents, and you will specify like a window of -3 of the optimal water contents and +3 of water content, and also like you will specify the maximum unit rate, or like if you keep when you're like hit a curve, so -3 and +3. So this is the window that you allow to be achieved in the field. We talk more about this, like how the quality check in the field look like. But the idea here now is when you want the strength performance, you will specify the uh, the uh, the water content to be a little bit dry of the optimums. So on the other hand, if you have a design that you want to focus on the hydraulic conductivities, so for examples, maybe earth dams. So, and examples for the previous topics on the strength, like, could be like a pavement. So you want the soils to be strong, to have a high strength, uh, towards the final grade before you get to the pavement that, you need to sustain heavy traffic load. Then, you need, when you compact the last lift, you need to specify the water content such that the contractor, we have to have a kind of like a design, a legal design on their hand when they like build when they compact the soils out there. They will know what kind of water they will follow you. They will follow the geotech engineers. They follow the recommendations from us. So that will be what they need to achieve in the field. So for hydraulic connectivities, for example, some earth dams. We want to have like a low hydraulic conductivities, right? In order to slow down the seepage going through our earth structure, and the hydraulic conductivities will have the best performance. So the lowest hydraulic conductivities will happens just reds of optimums. So the K over here stands for the hydraulic conductivities. Um, so in the design, for examples, now you want like the stability red. So you may want to have something like, plus 5% to negative 1% of the optimum water content. So this percent, like, is plus 5% of the optimum water content, something like this. So this picture here, I try to better illustrate by this figure. So this is what I mean, like in the design. Um, so this is the compaction curve that you establish from the lab test results. And based on your understand on what kind of performance you want, then you need to specify in terms of both water and also the density. So water is like, now the optimum water content. So this is the optimum water content. And this is the plus 3% now. And this is the minus 3%. So now pretty much like if you go back to the compaction curve, you got kind of like a window right there. And then you also cut off from the maximum relative density you want to get to. So yes, you want to have 100% is the best. What is the best always? What is the best performance? Uh, right at the water content, right at the optimum water content, and also 100% maximum dry unit rate density. So this point is always the optimum point is the best to achieve, but you need to realize that you will be very expensive to get to that point, and sometimes it's almost like impossible to get to that point. Um, because like it may takes a lot of compactions effort to get there, which means if you like take a long time to get there, which means it costs a lot of money, and in our business, time and it's money. So that's why to optimize the economic like budget or the economic reasons or feasibility of what's going on in constructions, you want to specify the requirements that are able to do the jobs. Meanwhile, you need to think of like the constructability for that. So that's why, like you have all these specifications. So if you have more like a typical project, for examples, like a story apartment buildings, you don't have like a too strict of requirements. Then like you could imagine, you have a wider range of a window to be acceptable, such that like the soil subgrade can withstand the lighter loading that you can have. But if you have another extreme, like a nuclear plant, that like the design life cycle for the building is not supposed to last for like a 500 years. Also, the design criteria may be like require that you can withstand like return period of 100 years earthquake loading. Then you need to make sure the substrate group is really strong. Then now, like instead of 90%, you may want to have design for something like 98% of relative density, and with a window of opening right there, maybe just like 1 or 2% of the water content. You want strength performance too, so you may want to specify it as just a little bit dry of the optimums. So those are the design part, design part you need to work on as a geotech, and you may take some times in your career to get to the point that you can use your PE stamp to uh, to 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 finalize your specifications, writing or design. But like everything is not here, so we need to understand all this compactions, behavior of soils behind the design. So going back to where we start, right? So hopefully like this picture like now makes more sense to you. So what happens is again from the field, we have the field materials for constructions to start with. Now we go through the whole, almost go through the whole lecture. You understand what we get is a compaction curve. It's a compaction curve from the lab testing. Water content and joining rate. So with this compaction curve, you can come up with the maximum dry unit weight, and also the optimum water content. And based on the design that you have, then you can also come with like a, a constructions, like a design window. Oops. So uh, what being like a pass and what being not passed in the field. So you can bring this like a piece of informations with the geotech design to go back to the field to do a quality control check. So again, like you will bring this back to the field. So what does it mean here? Is this is your QC check reference within like your your design or specifications. This means pass. So this is pass. Whatever like outside this gray area is not pass. So if you get like a point here, so which means like so after the constructor, they do their pass, they do their compactions in field. So as a geotech engineers, very likely as entry level, if you work as an interns coming up, or if you work as a first year geotech engineers, very likely you will carry nuclear gauge to the field and then like do a in situ right on the spot density check. So this is a device we'll talk a little bit more in the next slide, but this is device like you will take just like a 1 minute. You can tell you the density and also the water content. So you can tell you right away or where you're at on a compaction curve. So if you're here, that means it's not pass. But if you're inside the box, inside the gray area, then this is pass. So for examples, like if you get like so also this tells you if your understanding of your soil behavior, you also need to give recommendations to the field engineers on site. So if the test and you pass, then everyone happy. Then they can move on to the next lift, or like move on to the next locations for you to check, or for you for them to do the compactions. But when you do a test on site and the results turn out is not passing, then as a geotechnical engineers, the contractor will look up to you, ask for recommendations. What should they do now? So should they like keep compacting, or should the contractor kind of like wait for the sun to do their work, such that you can dry up the soil a little bit. At that time, as a geotech, you need to give your recommendations. So we know that like this is if you're right here, for example, let's look at the point that like you're not passing. So if you're at this point, if you're at this point, being not passed, what should you do? What should the contractor do? Should they keep compacting on the soils? If they keep compact on the soil, then we know that increasing compaction effort, you will go up that way. Yes, maybe you will get there, but what is the better solutions? In fact, if you find out like your compactions, your test results is right there, if you dry out the soil as a contractor, just dry out the soil, which means like they hopefully it's a sunny day, let the sun to do the work. If the soil is dry out, then you can get to the passing range. So that's maybe even more wise recommendations, more educated recommendations you can give out to the contractor. They will look into you and ask for what to do. Or if you have a compactions point right there, so what we need to do is like maybe like um, at that point you may want to add water to that, such that like you will get to the acceptable the passing range. If you have a failing point right here, if you keep like a adding or drying, keep wetting or drying, it doesn't help. So you get a, a test result right there. What you want to maybe recommend the contractor to do the more compaction effort. So like the line of optimums, we talk about that. If we increase the compaction effort, it will help us to go to the upper left corner. You will get there. So based on your test results, you can give appropriate recommendations on site as a technical engineers when it comes to the construction work for soil compactions. Okay, so the nuclear gauge, how does it work? So for the gauge, the way it works is this is a nuclear device that you will release gamma radiations. Uh, so so this is the nuclear gauge, and you got a detector right there. And also this is a source of radiations. And what we do is like you go on site, you punch your holes, and you lift down the like there's a little bit like a rod right here with the nuclear source or radiation source right there, and then you activate it. So from the time that from the source to the detectors, which is the photons path right there. So from the times that the detectors detects all the radiations, that's how the time that you measure from the device, it can help uh, to back calculate the density of the material that the photons are passing through. So that's the idea uh, of the nuclear gauge. And also you can detect the hydrogen's atoms, so you can also measure the water content. So that's the idea of using non-destructive nuclear density and water content measurements through the nuclear gauge. So this is the good thing about it is quick and it's portable. The whole thing like weighs about 100 pounds. And but the disadvantage of it is this is a very hard, expensive equipment, and because this is a new gear device, so a lot of regulations need to be followed when you use this gauge. But this is a very typical jobs that we are doing in our business now, and this is a very like common job for entry-level engineers. So, if you think you will go into the business of geotechnical engineering or even construction management, very likely your very first jobs or your very first year experience will be working with those like a nuclear gauge. So lastly, like future research, moving on, uh, business is instead of like doing a point discrete point of measurements. There's also ongoing research is the intelligence compactions, which means like where as it goes for the contractors, doing the compactions with the compactor. Uh, Nowadays, the technology is capable to do real time measurements, which like they have all this strain gauge, all this device with inside their compactor right there. So in the real times, as the machine passing through the soils, they can collect data, and then like pretty much at the end of the day, all this data can be translated to a passing, not passing kind of like indications, or whether you're getting the job done right at the spot and right at the time. So that will be kind of like the future of our business going down the road. I'm not so sure like when you would, how long it would take to change the whole practice. Maybe start you need to start with some building code or like practice code like modifications. But I guess at some point in the in the upcoming futures, maybe the next decades, I don't know how long it takes. Uh, Eventually, maybe that's the directions we are going up to. So with that, we finished the lecture of salt compactions. If you have any questions, please email me and I'll go to my office hour.